In this video, we're going to explore our slicing strategy again, but now we're going to include a third dimension and see how that plays a role. What we're discussing is a pyramid, like the one here, with an equilateral triangle as its base, each with 3 units of length. It is also 5 units high. Let's draw that over here. Our question is, what is its volume? Now, you might have memorized a formula for this kind of shape, but we're going to be able to determine that formula now from first principles by building an integral and evaluating it. The idea is going to be the same as what we've done to find areas. We're going to take this shape and divide it into slices. Those slices, if we look at it in 3 dimensions, are going to look like very small, thin, cracker-like shapes. Imagine a triangular cracker that we're stacking up with different sizes to build a pyramid. Our goal is going to be to find the total volume, but we're going to get to that by finding the volume of a slice. And again, we have to define some variables here to be able to talk about this slice, say, versus this slice. And there's a couple of ways we can do that. We're going to define this distance here down to a slice as h. Let's draw it like this. So if we imagine cutting through a little slice here, that'll be h away from the peak. You don't have to do it that way. You could also define h as the distance from the bottom. It works out with similar math. We'll just choose to do it from the top. If we do that, then if we take a look back at the 3D picture, the volume of the slice is going to equal the cross-sectional area times the thickness. This is our generic volume calculation for anything that has the same shape on the top and the bottom and just has a third dimension defined by a thickness. But that cross-sectional area is going to be the area of a triangle. Triangle area. And the thickness, going by the intuition that we've built before, if h is what we're calling the distance from the top here, then the thickness of the slice is going to be a small increment of h. If you look back at earlier examples, you'll see that same kind of structure with x and delta x, y and delta y. So our thickness in the formula here would be delta h. Now we get to the fun part. How big is a triangle when we draw it at height h away from the peak? Well, we've been given this handy fact that the area of an equilateral triangle with all sides of length a is given by this formula, a little a squared and something to account for the fact that it's an equilateral triangle. So if we call this length here a, that would be handy, except I don't want it in terms of a, I want it in terms of h. So how do we get from this picture to an actual formula for the area based on where we're taking our slice? That's where the 2D picture here comes in tremendously handy. We have a structure with h down to here, and we can see that our a is actually hiding as this distance here. Well, that a and h triangle is just a mini copy of the larger triangle, and what that gives us a similar triangle configuration, where we have one triangle which is a by h, and another triangle which is larger at 3 by 5. That construction and the fact that these are similar triangles lets us solve for a. So a over h, we'll do this calculation up at the top here. A over h is the same as 3 over 5. So a is going to equal 3/5 of h. All right, let's fill in these steps here one by one. If the area is root 3 over 4 a squared, delta h, the problem that we need to resolve is that this is an a, not an h. So we need to turn it into h's. Express with h's only. And we can do that now because our a value, how long each side of this triangle is 3/5 of h. So we keep the root 3, we keep the 4, we just expand the a squared to be 3/5 of h, all squared, close bracket, delta h. Perfect. If we do a sanity check now on the units, we'll see that we actually do have an area here. We take our length squared and we multiply it by the little bit of thickness, delta h here, or delta h in this diagram, and that'll give us a volume of a slice. Once we have that, we can easily express the integral. We're going to need this picture again when we do that, but it's basically going to be this formula inside an integral sign, giving us a total volume equal to the integral of our square root of 3 over 4 times, in brackets, our 3/5 of h, all squared, dh now instead of delta h. And we have to remember where we took our h's from. So wherever we took our slice to, we would take one slice at height 0, we'd slice, 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 and the last slice would occur, the h value for the last slice would be at h equals 5. So we always come back to, this is our variable of integration that defines what units the integral limits are in. And imagine just drawing each slice and asking yourself, what is the value of h on each of those slices? The first slice happens at the top. We called that 0 away from the top, so it's 0. The last slice happens at the very bottom of this triangle, and that is going to be at h equals 5. What this boils down to is that there is a lot of logic going on behind the construction of these integrals, which is sometimes hard to see, but it all comes back to the diagram, the definition of the variables, and usually some other little calculations like the similar triangles in this instance here. Take a look at the practice problems early if you're finding yourself struggling a little bit with this. Now that we've constructed our integral, we can evaluate it. In this particular case, it's probably worth simplifying because we have some nested parentheses here. So let's just tidy first. And in particular, we're going to bring all these constants out front. We have a root 3 over 4. We have a 3/5 squared, which would be 9/25. And then we have the integral from 0 to 5 of h squared. That doesn't look too bad at all, and it isn't. When at the end of the day, we have 9 root 3 over 100. The h squared, when we integrate it, becomes h cubed over 3 from 5 to 0. And notice we don't have to explicitly say h equals for these at the moment. If we have dh, then these are h values. I like adding them if there's ever any ambiguity or to emphasize a point, but they're not strictly required. Last but not least, we sub in our limits, and we end up with 5 cubed over 3, it's 125, minus 0. And if we start canceling things, we're going to end up with 3 and a 5, that'll be 15. The root 3 doesn't cancel with anything, and we'll end up with the 125 over 100 will give us a quarter. And that is approximately 6.495 cubic units of volume.